Good afternoon, students. We are going to study nuclear chemistry. I'm Dr. Betty, taking you through nuclear chemistry. Nuclear chemistry will involve the study of the chemistry of the nucleus, nuclear reaction, and radioactivity. Nuclear chemistry of the nucleus. An alpha particle scattering experiment carried out by Rutherford showed that the atom of an element contains positively charged hardcore at its center. This positively charged center part of the atom is called the nucleus. Now you can ask yourself, what is a nucleus? A nucleus is the central part of the atom, which is positively charged, dense, and linked. The whole mass of the atom is concentrated in it. The positive charge on the nucleus is due to the presence of protons. Let us look at the properties of the nucleus. Number one is the size or volume of the nucleus. Again, the alpha particle scattering experiment showed that the size of the nucleus of an atom is very small as compared to that of the whole atom. And experiments on the scattering of the neutrons have also shown that the radius of the nucleus can be given by the following expression. Which is the radius is equal to R naught A to power a third. Here R naught is equal to the constant whose value is 1.5 times 10 to power negative 15 meters. And the A is the mass of the element. The radius of the nucleus is of the order of 10 to power negative 14 meters, while that of the atom is of the order of 10 to power negative 10 meters. Usually the radius of the atom is bigger than that of the radius. The next property is the density. The density of the nuclear matter is the same in all the nuclei, and its value is very high and is of the order of 20 times 17 kilogram per meter cubed. The density is given by, or density is equal to nuclear mass over 4/3 times nuclear radius kilogram per meter cubed. The nuclear mass is in kilogram, while the radius is in meters cubed. That's why the units are kilogram per meter cubed. And the density of the nucleus has been found to be 10 to power 12 times that of the atom. Another property is the composition, charge, and mass of the nucleus. Nucleus is composed of protons and neutrons. That one you are all aware. Protons are positively charged, while neutrons are neutral. The nucleus is positively charged. Mainly, the reason is being that since it is composed of protons, which are positively charged, and the neutrons are neutral, therefore, the nucleus is positively charged. In case where it is not necessary to differentiate between the protons and the neutrons. We can call these particles nucleons. Nucleons is a constituent of atomic nucleus, that is, protons and neutrons. Another property is the emission of alpha, beta, gamma, and other particles from the nucleus. The newly formed element, when the nucleus of the atom of a radioactive element loses an alpha or a beta or a gamma or another particle, is called a daughter element. Usually alpha particle is a helium nucleus, which contains 2 protons and 2 neutrons, represented as helium with the atomic number 2 and atomic mass 4. Why? Because 2 plus 2 is equal to 4, the protons plus the neutrons. A beta particle has a negative charge, which is equal to -1, and the mass of the beta particle is equal to 0.0005482 times 0.166 times 10 to power -26 kilograms. When you evaluate this, is almost equal to a 0. Therefore, a beta particle can be represented as -1 and a mass of 0. A gamma ray has no charge and no mass. This means that a gamma ray is chargeless or neutral. The atomic number is 0. Thus, a gamma ray can be represented as 0 atomic number and 0 atomic mass. Gamma rays are usually high-frequency electronegative waves, like the X-rays, and have short wavelength. During gamma ray emission, the newly formed element has the same mass number and the same atomic number as the original, since it has a 0 atomic number and 0 mass number. Therefore, the newly formed element or the daughter element has got the same mass number and the same atomic number. Emission of a positron. When the nucleus of a radioactive element emits a positron, which has a 0 mass and a +1 charge, the mass number of the daughter element remains the same, since the mass number of the positron is 0, but its atomic number is decreased by 1 unit, since we have a +1 proton or atomic number. So it has to decrease by 1, as we shall see in the next lecture. An assignment I'm leaving you with is, what is the mass number and what is the atomic number of a given element or an atom? How do we calculate the atomic mass of an element having isotopes of different mass number? Let us consider the isotope of chlorine. This element has 2 isotopes, chlorine 35 and chlorine 37. If the abundance of these isotopes in nature is A% and B% respectively, then the atomic mass of chlorine atom is equal to percentage abundance of chlorine 35 isotope times the mass number of chlorine 35 plus the percentage abundance of chlorine 37 isotope times the mass of 37 or chlorine 37, all over the sum of the percentage of the abundance of the two isotopes. And in summary, it is A times 37. A is the percentage of 35 or chlorine 35, then plus B times 37, and B is the percentage of chlorine 37 over A plus B. Now, if A plus B is equal to 100, the above expression is given as atomic mass of chlorine atom is equal to A times 37 plus B times 37 over 100. This is also the same as A times 37 plus 100 minus A. Since the total percentage is always 100, so if we subtract off A, we shall remain with the next percentage of the next isotope, which is 37. So it is 100 minus A times 37 over 100. Let us look at the activities. Activity 1. Natural chlorine has two isotopes, chlorine 35 and chlorine 37. The percentage of the abundance of these isotopes is 37% and 35% respectively. Calculate the atomic mass or atomic weight of chlorine atom. How do we answer this? So the atomic mass of chlorine atom is equal to percentage of the abundance of chlorine 35 isotope times mass of that chlorine 35 isotope plus the percentage of abundance of chlorine 37 isotope times the mass of chlorine 35 over 100. This is the same as 37 times 35 plus 25 times 37 over 100. 37 and 75 are the percentage abundances of the two isotopes. So if you evaluate all these, you will get 35.5. Therefore, the atomic mass of chlorine atom is 35.5. The second activity is the relative atomic mass of copper is 63.5. Calculate the percentage of the isotope of copper 63 and copper 65 present in it. This one is evaluated as, or is calculated as, if the percentage of the first isotope is supposed to be equal to X, and the percentage of the second isotope will be 100 minus X. I told you if it is in terms of percentage, the total percent is 100. If the first percent of the first isotope is X, then the second percent of the second isotope will be 100 minus X. The relative atomic mass of copper is given to us as 63.5. Therefore, 63.5 is equal to X times the atomic mass of the first isotope, which is 63, plus 100 minus X times 65, the second isotope. And 100 minus X is the percentage of the second isotope. All this over X plus 100 minus X. If we solve this equation, we shall find out that X is equal to 75, and 100 minus X, or 100 minus 75, the answer will be 25%. Therefore, in summary, the percentage of the first isotope is equal to 75, and that of the second isotope is equal to 25. Therefore, in conclusion, we have gotten the percentages of the two isotopes, which is 75 and 25%. The last activity, activity 3, nitrogen 14 and nitrogen 15 present in ordinary nitrogen are in the ratio of nitrogen 14 over nitrogen 15, or nitrogen 14 to nitrogen 15 is equal to 272 to 1. Calculate the atomic weight of nitrogen. So this is the same as the atomic weight is equal to 14 times the 272 plus 15 times 1 over the total ratio is equal to 14. Therefore, the atomic weight of nitrogen is equal to 14. Lastly, I can leave you with this activity. Number 1, a sample of ordinary neon is found to consist of neon 20, neon 21, neon 22 isotopes in the percentage of 90.92%, 0.26%, and 8.82% respectively. Calculate the actual atomic weight of neon. The second activity is naturally occurring carbon consists of 2 isotopes, namely carbon 12 and carbon 13. What are the percentage abundances of these isotopes in the sample of carbon whose atomic weight is 12.0112, assuming that the masses of carbon 12 and carbon 13 are 12 and 13.00334 mu respectively. Next time, we are going to look at forces which operate inside the nucleus of an atom.